Look at the size of this platform. The Caterpillar C175-16 is built for mission-critical power generation. Data centers, offshore rigs, and critical infrastructure need maximum electrical output, crammed into the exact same mechanical room or skid space that used to hold much smaller engines. Past generator platforms hit a hard ceiling. You cannot indefinitely increase the physical footprint of an engine block to get more power. Eventually, you run out of room. This specific block displaces 85 liters. Out of that fixed volume, Caterpillar engineers are extracting up to 3,500 horsepower. Getting 3,500 horsepower out of 85 liters presents a strict metallurgical problem. To make that power, you have to inject an enormous amount of fuel into the cylinders. Burning that much fuel inside a confined space generates extreme heat that will literally melt forged steel pistons. To survive that extreme thermal load and break the horsepower ceiling, you must manipulate the air's chemistry before it reaches the combustion chamber. This is a visual representation of the power equation. Volume multiplied by density dictates total oxygen availability. Since the 85-liter volume is a fixed physical dimension, the only way to safely burn more fuel is to increase the density of the intake air. Density means packing more oxygen molecules into the exact same cubic inch of space. More oxygen means the engine can combust a larger volume of fuel per cycle, while keeping temperatures inside the safe operating window. The C175 achieves this density through 4 strict stages: filtration, compression, cooling, and induction. Every liter of air must survive this exact sequential path. The ADEM A4 electronic control module monitors sensor data across every single one of those stages to protect the block from destruction. If you approach this engine diagnosing for airflow, you will chase the wrong faults. You have to diagnose for density. This CAD model maps the atmospheric intake flow path. The first stage begins here, where atmospheric air is drawn into the high-capacity dual-element air cleaners. This dual-element filtration provides the volumetric baseline. A restricted primary element immediately starves the 2-stage boost system downstream. This diagram shows the first major ECM checkpoint, the turbocharger compressor inlet pressure sensor. The ECM calculates an average pressure across both banks to detect plugged air filters long before the turbos operate outside their mechanical limits. This is the diagnostic table for the analog sensors. If that calculated average drops, the ECM logs a 2738-3 or 2738-4 code, flagging a drop in compressor inlet pressure. On the C175, air filtration dictates the survival of the turbochargers. Without that initial volume of air, the downstream compression fails. This graph plots engine load against boost pressure. A single turbocharger struggles at low RPMs and lacks capacity at high loads. The C175's 4 series parallel turbochargers create a consistently high, flat boost line, delivering instant response at idle and massive volume at full output. Caterpillar mounted these 4 turbochargers outside the engine's central V, giving technicians direct access for maintenance. Compressing that much air to match 26,000 psi of fuel rail pressure has an intense physical consequence. Squeezing air molecules generates massive amounts of heat. The turbochargers successfully provide the required air volume, but the heat they generate physically expands the air, ruining the oxygen density. To recover density, the hot compressed air is routed into the separate circuit aftercooler, or SCAC. As the SCAC core strips away thermal energy, the gas physically contracts. Oxygen molecules pack tightly together, drastically increasing the actual mass of air available for combustion. This charge air cooling system is completely independent from the engine's dual-pass jacket water circuit. The jacket water cools the block metallurgy, while the SCAC cools the air. The two fluids never mix. This diagram illustrates how the ECM monitors that SCAC efficiency, utilizing dedicated sensors at the water pump outlet to track both coolant pressure and temperature. Without the SCAC functioning perfectly, the mechanical work of the turbochargers is neutralized by thermal expansion. This cross-section of the cylinder head shows the final delivery stage. The dense, cooled air is inducted directly into the cross-flow heads. This architecture ensures incoming intake charge never mixes with exiting exhaust gases, minimizing pumping losses and maximizing efficiency. Right before combustion, the ECM takes its final readings. It checks the air intake manifold pressure sensor to confirm total boost. It immediately pairs that pressure reading with the data from the air intake manifold temperature sensor. By calculating these exact pressure and temperature values together, the ADEM A4 determines the absolute oxygen density in the manifold and uses that figure to command the high-pressure fuel pump. The control logic completely relies on those manifold sensors. That final calculation dictates whether the engine can safely inject enough fuel to generate 3,500 horsepower. Consider a field scenario. A C175-16 generator set is experiencing a noticeable loss of rated electrical power, and exhaust temperatures are climbing under heavy load. The diagnostic table shows an active 17203 code for intake manifold air temperature sensor voltage above normal. The engine is pulling in hot air. The most common reaction to high heat and low power is to immediately condemn the turbocharger as the root cause of the failure. But if you replace a $40,000 turbocharger based on temperature alone, you will likely return a failing engine to the customer. Look at the remaining data. Normal boost pressure proves the turbochargers are perfectly compressing the required volume of air. The actual fault is downstream. A fouled SCAC core is failing to remove the heat of compression, destroying the air density. To protect the turbine metallurgy from those rising exhaust temperatures, the ECM initiates a staged derate. It incrementally cuts fuel delivery by 5% at a time, keeping the electrical bus stable while forcing the temperatures back down. Operating and maintaining the C175-16 requires abandoning the basic airflow mindset. By understanding and diagnosing the 4 stages of air density, you isolate the true fault and protect the massive output of this platform. Consider a field scenario. A C175-16 generator set is experiencing a noticeable loss of rated electrical power, and the exhaust temperatures are climbing under heavy load. When you connect to CAT-ET, the diagnostic table shows an active 17203 code for intake manifold air temperature sensor voltage above normal. The engine is pulling in hot air. The most common reaction to this combination of high heat and low power is to immediately condemn the turbocharger. But if you replace a $40,000 turbocharger based on temperature alone, you will likely return a failing engine to the customer. You have to look at the second half of the dataset. In this scenario, the boost pressure reading is completely normal. That normal boost pressure is absolute proof that the turbochargers are operating perfectly, compressing the required volume of air. The fault is entirely downstream in the cooling circuit. A fouled SCAC core is failing to remove the heat of compression, destroying the air density before it reaches the cylinders. To protect the turbine metallurgy from those rising exhaust temperatures, the ECM initiates a staged derate. It incrementally cuts fuel delivery by 5% at a time, keeping the electrical bus stable while forcing the temperatures back down. Operating and maintaining the C175-16 requires abandoning the basic airflow mindset. By understanding and diagnosing the 4 stages of air density, you isolate the true fault and protect the massive output of this platform.